Okay, 2.2. We're looking at the same stuff that we did before. We were looking at the slope of a tangent to a curve, and we saw that that was also the instantaneous velocity. So we could talk about a tangent slope for a tangent line. We could talk about instantaneous rate of change. And it doesn't even have to be limited to velocity. It could be whatever the change in y over the change in x is. Guys, these things are called the derivative. It's the derivative. So, you saw that you had these two forms, and what you were finding before was the derivative. Now, notice that the derivative can be written very, very subtly and nicely. One form is to say f prime of x. Now, what kids are going to notice immediately is they're going to make a comparison and say, now wait just a second. Right here, you had this limit and you had a everywhere. And I'm looking right here and it's just x's. Guys, it's all the same at the end of the day. Remember, a was an x value, wasn't it? So wherever you had an a, you could replace it with whatever variable you would like. It's just that up here, if somebody would say, what did you find at the top of the screen? Well, that would have been f prime of a. When x equaled a, that would be the derivative. That would be the tangent line slope at x equals a. It would be the instantaneous rate of change in y over change in x, whatever units you have, that's what rate of change you're really talking about. And then right here, this should look a little bit more familiar. Guys, I'm going to let the cat out of the bag. We've been doing this problem the difficult, long way. There are many problems where you have to do this with a limit, working it out. Some of you already know, I'm sure, that there is a shortcut. Go to the back. There's a beautiful, powerful, delightful shortcut. You could say, what if you had f of x equals cx to the n? You know what you're really going to do? You take your power, when you take your derivative, take your power and drop it down. Drop it like it's hot, multiply to that coefficient, and then you subtract your power by 1. For example, take a look at number 3 here. I know we're doing it out of order, but I want to do this fast. Could we find the derivative working this thing out with a limit? Of course you could. But if you see x to a power, hey, that's the best news you're going to have all day. You're going to say, hey, all I have to do is take that power of 8 and drop it down. What's your new power? 7. You drop the power down by 1. You subtract 1. And we all know that 5 times 8 is 40. You're done. You found your derivative. If you work that out with your limit, you'd get the same answer. Oh my God. Unbelievable. That's pretty cool. Hey, take a look here. Kids will say, Mr. Dobner, wait a minute. You don't have a power written out. Yeah, you do. This is 5x to the negative third. So guess what? F prime, you'd say, well, I've got to bring the negative 3 down, and then I subtract 1. What's negative 3 minus 1? Negative 4. So you'd get negative 15, x to the negative 4th, which is fine. You could write it like that. Or you could also write it as negative 15 all over x to the 4th. Then let's take a look at number 5. You'd say, well, you just have a 4. You don't even have an x there. By the way, I'll give you a hint. Isn't this like the graph y equals 4? So look at this. Here's a horizontal line, y equals 4. What's the tangent line slope of that? Just look at that, a flat horizontal line. It's 0. Oh, wow. You know what? F prime of a constant is 0. Kids would say, well, how in the world could you ever get that from your rule up here? Well, here's my point. Let me just take this off to the side here. wouldn't this be, you'd say there's no x. Yes, there is. It's x to the 0, isn't it? And then you'd say, yeah, which is 1. But if you brought your 0 down, then you'd say, well, then subtract. Well, what's anything multiplied to 0? It just wipes out, doesn't it? But more to the point, just memorize the derivative of a constant is 0. Now, you take a look at number 6, you'd say, well, wow, isn't this really x to the, what's the cube root of x? It's x to what power? 1/3. Hey, what's the derivative? What comes down? 1/3. And now you subtract 1. What's 1/3 minus 1? Negative 2/3. You could leave your answer like that, or you could even bring your negative power down, and that's what you get. I don't know about you. I kind of like doing the derivatives this way, don't you? Isn't that a lot nicer than working it out with the limit? And that begs the question. Let's be really honest. You can think, so why did you and Mr. Clifford even teach us this other method? I mean, show us this, and that's the way to do it, right? Listen, you're going to see problems very soon, like tomorrow, where this shortcut doesn't apply. And then you'd say, well, how do I find a derivative? You got to go back to the definition. You got to do the limit. So listen, most of your derivatives, I'm happy to say, are actually going to be beautiful shortcuts. But there is the need to understand the limit definition. That's the official definition. And thinking of a derivative as a limit, guys, is super important. It will explain some behavior about derivatives down the road. Let's revisit example 1, where you can think, well, holy smoke, find the derivative. I don't want us to have to do the limit right now. How about we just use the smart way? My goodness, let's be clever here. F prime of x. It doesn't take long for kids to say, well, bring your coefficient down, and that's 2 times 3. What do you get? 6. So that's 6x. What's the derivative of minus 12x, do you think? Minus 12. I mean, you bring the 1 down, and then you've got x to the 0, right? Take a derivative of an x, it just goes away, in other words, right? And then what's the derivative of this constant? It's 0. You don't even have to write it down. Oh my gosh, this is cool. Wow, we don't have to do a limit anymore. Wow, this is pretty neat. So they're saying, hey, if you know that your derivative is this thing right here, they're saying, please tell me the slope of the tangent line at this point where, hint, 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 x is equal to 3 and your y value is -1. Wow. Well, guess what I'm going to plug in for x? I'm going to plug in 3. And we know that 6 times 3 is 18. 18 minus 12 is a 6. The slope of that tangent line is 6. Right? By way of comparison, if instead I told you, oh, did you know that this y is actually a position function, then the derivative would be the instantaneous velocity there. Right? So that's another way to look at it. Okay, we doing okay? Well, then they're going to say, find the point on the graph at which the tangent line is horizontal. Well, wait a minute. If the tangent line is horizontal, you might remember Vux and Hoy. Horizontal lines have what kind of slope? 0 slope. Wow, we need that. The equation would always look like y equals a number. And look, we've got f prime of x is equal to 6x minus 2, or 12, sorry. And you'd say, plug in that slope of 0. Plug in that slope of 0. And then you solve. So I'm going to add a 12. And I'll have 12 is equal to 6x. Divide by a 6. What's x? X is 2. Now, is that my final answer? That's not a point, is it? That's an x-coordinate of a point. It's an x-coordinate of a point. So I know that at the point 2 comma something, and then you could say, well, look, back at the screen, if we plug in at the top of the screen, pardon me, if you were to plug in a 2 for your x, 2 squared is 4. 4 times 3 is 12. 12 times 2 is 24. Look, 12 and 8 add up to 20. 20 minus 24 is negative 4. It's this point where if you drew in a tangent line, you would actually have a horizontal line. We doing okay? All right. So, wow, this is pretty cool when you can go ahead and take quick derivatives. Let's jump back in for number 7, following the directions. For part A, they say take a derivative. Part B, find the domain. What x values can you plug in to find a derivative value? And then for part C, find all points on which the tangent line is horizontal. And then D, write the equation of the tangent line at x equals 4. So, wow, let's keep going here. We've got f prime of x. Here's for part A. What do we get? Help me out. 8x minus 16. Hey, that's cool. Take a look at 8x minus 16. Is there any x value when you plug it in, you get a rule of arithmetic that would break? You'd say you can't do it. You'd get an error if you typed it into the calculator. Your domain's all reals. You can plug in whatever x number you want. You could find a tangent line slope or an instantaneous rate of change. Okay? For part C, they're going to say, where is this going to be horizontal? Well, guess what I'm going to let f prime equal? 0. And so very often kids will say, oh my gosh, you can pretty much just see the solution. You can see it's x equals 2. But we need a point, don't we? It's 2 comma. Well, if you were to plug in a 2 here, 2 squared is 4. 4 times 4 is 16. 16 times 2 is 32. So 16 minus 32 is negative 16. Negative 16 plus 1, I'm getting negative 15. All right, we good? And then they'd say, well, write the equation of the tangent line at x equals 4. Well, wow, we've done that before, haven't we? We have to be real careful here. We've got to, first off, say my derivative is right here, but now I want to know the tangent line slope at 4. And if I plug that 4 in, 8 times 4 is 32. 32 minus 16 is 16. That's your m. And of course, to get the equation of a line, guys, we want to go back to point slope. And as we do that, I hope you can see real quickly that we could find 4 comma something. 4 squared is 16, and 16 times 4 is going to get you, what's that? 64. Minus, 16 times 4 is also 64. So it's just a 1, isn't it? You've got the point 4 comma 1 there. Well, what are we talking about? This is your x1, y1. So I'm going to say y minus a 1. And here's your x minus 4. But your slope is 16. And there you have it. Okay, that's your equation of your tangent line. Okay, tell you what, as we take a look real quickly at number 8, for part A, I guess I just want to tell you, this is x to the 1/2 minus an x. A square root is just going to be the 1/2 power. Help me take the derivative. What do we get? 1/2 x to the negative 1/2. And what's the derivative of just an x? Minus 1. God bless you. So, what we've got right here, if you want to write it out, you could bring this x to the 1/2 down, and that's really a radical x, and that's your derivative. That's how you can find a tangent line slope. Okay? So at this point, guys, as we continue on, they're going to say, what's your domain? Now, your domain actually is first always going to be hit off from the beginning. The original function. If you don't have a point, can you draw a tangent line at a non-existent point? No. So the original function, that domain is going to first come into play. What's the domain of the original function